Speak to the earth, and it shall teach thee. You are listening to Brothers of the Serpent podcast.
And welcome back, ladies and gentlemen, boys and girls, angels and demons, monsters and serpents, to Brothers of the Serpent podcast, coming to you not live from the 10 by 10 by 10 tangent cube of science, nestled amongst the dusty bones of an ancient seabed high atop the Edwards Plateau here in Texas, where it's finally getting warm. Finally. It's getting a little warmer.
Yeah, sadly, yes. Sadly,
yeah.
Yes.
We went past the equinox, and it's definitely, we can tell, that spring is here. Everything is blooming. But speaking of the equinox, we have an awesome freaking interview for you guys. It is an interview we did with Mr. Randall Carlson, which is amazing. And I'm going to read an introduction of him. I got this from Graham Hancock's website. So, but we have some other stuff to tell you about this interview after I read this introduction. So most of you know this, but I'm going to read it anyway. Randall Carlson is a master builder and architectural designer, a teacher, geometrician, geomythologist, geological explorer, and renegade scholar. He has 4 decades of study, research, and exploration into the interface between ancient mysteries and modern science. He has been an active Freemason for 30 years and is past master of one of the oldest and largest Masonic lodges in Georgia. He has been recognized by the National Science Teachers Association for his commitment to science education for young people. The acclaimed 1997 TBS CNN documentary Fire from the Sky was based upon his research into Earth change and catastrophic events. He has organized several dozen field expeditions documenting evidence for catastrophic Earth change. He has received academic recognition for outstanding work as a student of geology. His work incorporates ancient mythology, astronomy, earth science, paleontology, symbolism, sacred geometry and architecture, geomancy, and other arcane and scientific traditions. For over 25 years, he has presented classes, lectures, and multimedia programs synthesizing this information for students of the mysteries.
Fascinating library or body of work.
Yes, absolutely.
Yeah.
So,
sadly, when we began the interview, it began just this way. And yet, due to technical difficulties, I think on our end and bad internet connection, when we introduced Randall and then he says hello, it was like, meep, 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 meep.
Yes.
Couldn't understand anything.
Yeah.
So we overcame adversity and called him on a landline.
Right.
When all new technology fails, use a landline.
Right.
Use old technology.
Right. So we tried the internet connection. We got that working, but it was just so glitchy. And then we ended up just saying, you know what, Randall, let's just call you on your landline, and after that, he sounded great. Yeah. So
thanks to Randall for putting up with all of that in the beginning of the show.
Yeah. Thanks for sticking with us.
Sticking it
through all the technical difficulties. But
yeah, that cataclysmic initial start there.
Yeah. That's right. It was a total cataclysm at the beginning there. And the Watcher was present for this show. He is not present now when we are recording this intro, but he was there and he was on the line with us for most of it, be able to listen to Randall. And so I can't introduce him now because he's not here, but he was there and he was paying attention and he had some great input towards the end. So,
yeah. All right. So here you go, folks.
That's right.
Randall Carlson.
So yeah, what have you been?
Sure, sounds good.
What have you been working on most recently? What's your what aside from your day job? What are you looking at most recently with all of this stuff?
Well, let's see. Mostly, I guess lately I've been looking a lot at volcanism and solar-related things. I'm trying to learn more about the sun and its role in global change. So yeah, and volcanism. So those have been two things that I felt were kind of weak in my overall concept of global change forces. So I've been spending a lot of time learning more about both of those things, which are actually quite interesting, as it turns out, and very significant and critically important in understanding the kind of things that have caused global change in the past, are causing global change now, and will continue to do so into the future.
Yeah, I mean, to me, it's always seemed like the sun, you know, if you look at the whole system, you're like, yeah, so the sun is everything when it comes to global climate change and anything like related to that. I mean, the sun is the reason we have climate, right? We wouldn't have climate without it. We would be a frozen ball of rock solid ice. Even the gas would be frozen solid without the sun.
Yep, that's right. So, yeah, I think that's going to be, we're going to find out. Well, what's been going on essentially the last few decades is that solar scientists have been learning more and more about the sun due to all of the various satellite-based observations that have been underway for the past quarter century roughly, and have been learning a lot of things that are now known about the sun that were not known 25 and 30 years ago in the pre-satellite era. And what that is basically revealing is that the sun is a much more dynamic celestial body than anybody had assumed a generation or two ago, and it has tremendous significance and bearing on the question of climate change. But the problem is that generally the sun is being discounted in all of the grand dozens of computer models that have been done to create climate projections based upon carbon dioxide forcing. The sun has basically been relegated to the sideline, if not eliminated or ignored altogether, which is one reason why the model projections are constantly coming out wrong.
Right.
Yep.
Yeah, I completely agree. So what exactly in volcanism are you looking at? Are you just looking at how it may, because I know that you've talked about how, large impact events may cause like this massive resurgence of volcanism all over the world. Is that what you're talking about, or?
Well, yes, I definitely think there's a relation, because yes, big impacts do cause volcanism, and it could be that a lot of the volcanism from the last 10,000, 11,000 years is a consequence of the series of impacts that now appear to have bombarded this Earth at the end of the last ice age, because there was such tremendous geomorphic work that went on the surface of the Earth that it had to have effects in the subterranean regions of the Earth, because you had I did the calculation once. I don't remember off the top of my head. It was an enormous number, calculating the number of metric tons of glacial ice that were mantling North America during the end of the last ice age. An enormous, just inconceivable amount of weight. Well, obviously, if you've got an ice sheet that reaches from the Atlantic Ocean to the Pacific and from the northern United States to the Arctic Circle and maybe up to 2 miles thick at its center, it's going to weigh a lot. And because of that weight, what it does is it pushes the surface of the Earth down into the mantle. There's a bending of the surface of the Earth called isostatic depression, and basically it's just like the analogy I always use is just like if you sit down on a chair with a cushion. Are you guys sitting on chairs right now with cushions?
We are.
Absolutely.
Okay. Well, so your asses right now are demonstrating the principle of isostatic depression. So if you were to stand up, the cushion rebounds to some extent, right?
Right.
And then if you sit down, it depresses, right? Well, the weight of your body is causing isostatic depression of the cushion. And then when you stand up and your weight is removed, then the cushion will rebound in a process called isostatic compensation or isostatic rebound, right? So this has been studied. We were talking about the Bonneville flood earlier, and for example, if you go into the basin of the Great Salt Lake around Salt Lake City, you can see shorelines up on the mountainsides. Now the shorelines, you're like just north of Salt Lake City, you can look up on the sides of the Wasatch Mountains, and you can see several shorelines up there that are fossil remnant features of the presence of Lake Bonneville that once existed there. Normally, if you've got a static body of water and it's standing, you know that if you've got a lake or anything that you fill up, a tub, anything, any container, you know that the surface of that water is going to be level and create a level line around the rim, right?
Yeah, that's right.
It's going to be level, right? Unless there's some disturbing force. Now, what geologists actually early noticed on was that the shorelines from Lake Bonneville were not level. And the reason they weren't level is because when the lake drained away, it was a combination of draining away through catastrophic flooding, and then the remnant water evaporated away. But what happened was the weight of that water, 1,000 feet of water, had literally depressed the surface of the ground there by several hundred feet. So when that was gone, that came back. And when that came back, what it did is it raised up in the middle. You can kind of picture in the middle of the lake where the water was the deepest, that shoreline now, that fossil shoreline, was higher than it was at its two ends. Does that make sense? Because if the land had stayed where it was, there would be an even rim of shoreline around the high water mark of the lake. But because the land didn't remain stable, it rose, and where the water was the deepest, the land rose the most, see? So now the shorelines are tilted, and that was a clue. See?
So you mean,
and that's isostatic.
So you're saying
that's isostatic rebound.
The weight of the water itself is what
it's the weight of the water itself.
Ah.
Now, if 1,000 feet of water can cause hundreds of feet of depression, imagine what 10,000 feet of ice could do.
Yeah.
So if, in fact, I have photographs in my slideshows here, and maybe I'll show some of those there in Colorado during one of the lectures, but where you can see their aerial photographs where you can see so it's almost like a staircase of shorelines around Hudson Bay. The Hudson Bay up in Ontario was where the glacial ice was the thickest, so that was the lowest spot. And so it makes sense that area right there now is filled by seawater because it's a naturally low depression, and it is actually still rebounding. It's still coming back, although most of the rebound took place in the first few millennia after the ice was removed. But you see, so you've got this vertical movement of the Earth's surface. Now, when you picture when that land is coming back or when that land is being depressed, what's going on below the surface? See, enormous patterns of stress are being generated in the lithosphere, in the rock masses below, right? And in some cases, there are fault lines, there are fissures, there are places where there's magma moving through the rocks, right? So it's almost like, imagine it's almost like a deep pressure massage or something, that's happening when this weight builds up on the land and then when it transfers back into the ocean basin. So we know that there was enormous volcanic eruptions during the deglacial process because the massive flooding from the meltwater of the ice sheets that backflooded into the still water basins and was preserved as layers. In those layers, there are thick deposits of volcanic ash. So you can look at those and you can interpret that and understand that, you had these amazing, huge floods sweeping over the land, and wherever they backflooded into a normal, say a tributary stream or something, and then flowed back out, they left layers of mud. And there are places where you can see 30, 40, 50 layers that are built up called rhythmites. And each one of these was like a pulse of sediment-laden meltwater that gushed in, slowed down, reversed course, and then flowed back out, and in the process left this layer. So you can go and you can find exposures of these layers, and in those layers, sandwiched between them, you can find thick layers of volcanic ash. Wow. So right there, that tells you almost like it's a double catastrophe going on. There's massive flooding at the same time. There's massive volcanic eruption. So no wonder, the megafauna went extinct.
Yeah,
right.
So I remember reading about this. We have this extinct volcano nearby. It's near Austin, which is about 2 hours from where we live in Texas. And when we were looking into that, we went on a little field trip, Snake Bros field trip, to go check it out. I was reading about the way these volcanoes erupt, and it was talking about the viscosity of the magma and how when it's under a lot of pressure, there are all these gases that are, of course, like dissolved into it. But when it, say, reaches an upper chamber and the pressure becomes less on the magma, these gases start to precipitate into the magma, and that's what causes these explosions. So I can imagine when the isostatic rebound is happening, it's releasing all this weight off the magma and allowing these gases to come out and Probably.
Yes.
Oh, yeah.
All kinds of explosions and stuff.
Explosive volcanism. Yeah, that's exactly right. So that's, what I'm looking into to try to understand. But the scenario now, of course, and it's purely hypothetical because nobody knows yet, because this is cutting edge information. The realization that that there are cosmic deposits that are found at these same time zones as when the flooding is going on, when the mass extinction is going on, when the volcanism. What has to happen is a detailed chronology needs to be worked out to try to figure out exactly what happened. But here's what makes sense to me, and it's sort of consistent with what I think most of the evidence is that whatever brought on the Ice Age, which is still a whole other question itself, it led to this massive accumulation of ice. That's not explained. Then how you get rid of that massive accumulation of ice in a few thousand years is not even close to being explained. In the old days, you had the comfortable assumption that it might have taken 30 or 40 or 50,000 years or longer for the ice to gradually melt away. But then when radiocarbon dating comes along in the 50s, and after you've accumulated a couple of decades worth of data, what became apparent was that no, the melting was way quicker, way quicker than anybody had imagined. And what happens is that the window during which the ice is at its what they call the late glacial maximum, which is say between 15 and 20,000 years ago, and the time when the ice is gone, has shrunk from 30,000, 20,000 to 10,000. And then to 8,000, 8,000 years, then to like 5,000. But then the problem is that within that 5,000 or 6,000 years, it's not a uniform melting. The melting is occurring in these massive pulses. You see, massive pulses of meltwater are being discharged back into the ocean. It's not a continuum. It's not a smooth process. You understand what I'm getting at here? It's not, the ocean rose in discrete jumps, and that rising of the ocean in these discrete jumps is because of the fact that the melting was occurring in these discrete pulses. There's what it appears to me now is that there were likely 3 massive pulses of meltwater into the ocean. And it was the third one at 11,600 years ago that was finally the death knell. The first 2 did not end the Ice Age per se. And in fact, the second one, which would have been about at the Younger Dryas, about 12,800 to 12,900 years ago, appears to have actually pushed the planet back into the full depths of cold that existed during the late glacial maximum. So then you had 1,300 years between, say, in round numbers, 12,900 to 11,600 years ago. Then at 11,600 years ago, you had another massive meltwater pulse into the ocean. The oceans rose very rapidly over a short period of time. And at that point, the whole climate of the planet shifted gears, and we moved into the interglacial age. It almost like kickstarting a bike or something. It took 1, 2, and then finally on the third one it took, and the planet was jolted out of the depths of the Ice Age. All the ice melted away that was mantling northwestern Europe, that was covering Canada. Like I said, now bear in mind, because of the fact that sea levels were 400 feet lower, the ice mass was all the way out to the existing coastline.
Oh, man.
At that time, which is not where it is now. See?
Right.
But then when you get south of where the ice sheets were, obviously in Texas, Texas was not under the ice sheet.
Right.
Nebraska was earlier, much earlier Ice Age actually did come down to Nebraska, and that is referred to traditionally as the Nebraskan period. It was the Kansan, Nebraskan, the Wisconsin was the last one, the most recent. And it's because it's named after where the deposits of these glaciers were most studied in depth. Right. So in the Kansan, obviously, they were looking in Kansas, and in Nebraska, they were looking in Nebraska and Wisconsin. They were studying deposits in Wisconsin. Now, the last Ice Age was not the biggest mass of ice. Earlier cycles of glacial ages actually were even larger than the mass of ice that was at the end of the Wisconsin. And see, in the older models, the assumption was is that the Wisconsin lasted about 100,000 or 150,000 years. That means it would have begun, somewhere between 120 and 150,000 years ago, that the ice mass slowly grew, that it was stable for tens of thousands of years, and then, somewhere between 25 and 50,000 years ago, it began to melt away, and then finally, by 7,000 or 8,000 years ago, it was gone. But that model isn't even close to what is now known about the whole process, you see. So what it has done is it just has presented us with a profoundly complex mystery about what happened. I mean, because one of the big mysteries, it was first identified in the early 70s. Once it had accumulated enough radiocarbon dates, a couple of things. One was that, wait a second, we've found pollen and organic material in Canada in areas where the ice was a mile thick 15,000, 20,000 years ago. But this pollen and these seeds and this organic material is dating to 35 to 40,000 years ago. So there's a problem. Right there, you see what the problem is.
Yeah,
right?
I see the problem.
That suggests, a major problem. Wait a second. So these glaciers were gone or mostly gone at that point, at that time. So wait a second. What happens to the model of a long, continued period of ice accumulation and dissipation that lasts 100,000 or 150,000 years? Because suddenly now, right in the middle of that thing, it wasn't there. The ice was not there. So that's one of the problems. The other problem was realizing that the ice had disappeared as quickly as it did, raised the question of, well, in order to melt ice, you have to have energy. Now, where is that energy coming from?
Right.
And that question has not been answered yet. See?
But you've been following the work of Firestone and West and these guys with the Younger Dryas impact hypothesis, right? And I know you've been following it very closely.
I'm not only following it, I predicted it probably 15 years before they published their first paper.
No, right.
Because I had concluded that because, see, this thing with it was called by scientists in the early 70s, it was called the energy paradox. And I think I first probably came upon my interest in ice ages goes back basically to, I would say my obsession with understanding that goes back to the 70s. And at that point is when I found, not when it was first published, but maybe 3 to 5 years after there was first published, these studies on the energy requirements. And let me pull something up here for a second. It was one of the key scientists, John T. Andrews. He was with the Institute of Arctic and Alpine Research at the University of Colorado at Boulder, and he was one of the first guys that really got into this, trying to understand the deglaciation process. And this is what he found. He looked at he used the period from 12,000 years ago to 7,000 years ago. This was in the early 70s. Now, they've recalibrated the radiocarbon dates, so these dates are actually a little too young. Where he's saying 12,000 to 7,000 now would be, say, probably maybe 8,000 to 13 or 9,000 to 14,000 years ago. But it's a 5,000-year window, right?
Right. So
this is what he says is the average. Now, this was published in 1973 in Arctic and Alpine Research, which was a specialist journal for glaciologists primarily. Were the ones who published in it when glaciology was really becoming an established science. He says the average marginal recession between 12,000 and 7,000 BP, which you'll see a lot in the scientific literature, which just means before present.
Right.
Okay, 12,000 and 7,000 BP is estimated at 260 meters per year and varies little between the northwest and southern margins. Now, 260 meters per year, that's times 3.28, so that's, it's over 850 feet a year of recession. So now imagine, let's see, here's now you can visualize the problem. You're standing let's say you're standing up in central Minnesota, actually right about where I grew up, as a matter of fact. You would be standing right at the southern edge of this huge ice sheet that extended for 1,500 or 2,000 miles or so to the north, And it would have been a huge, vast, probably where you were standing at the ice margin, it would have been a wall of ice 500 to 800 feet in thickness. Because you typically see the big glaciers when they're coming and calving into the ocean, even in modern times. But it would stretch back. I mean, it was as far as the eye could see, and it would just extend, from, say, central Minnesota all the way up to the Arctic Circle.
Right.
Right. So you're standing there and you're looking at this thing, right? Now, to get rid of that, this is one model. Now, this is not saying this is exactly what happened, but hypothetically, it would be the same as this, right? That it would go 850 feet every year. It's melting back 850 feet. Next year, 850. So if you're standing at the edge of the thing, and assuming you're not going to get swept away by meltwater floods coming off, right? If you have some way of not drowning, right?
Right.
You're standing there this year. Next year, it's going to be 850 feet further north. The next year after that, it's going to be 1,700 feet. And then each year, for the next 5,000 years, it's receding back 850 feet. On average each year in order to be gone that quickly. Does that make sense what I just was? Okay, yeah. So now imagine what we've learned today from the times of the ending of the Little Ice Age, which was roughly 200 years ago, 150 to 200 years ago. I think you could say the last phase of the Little Ice Age ended in about 1850, right? Now, during the Little Ice Age, which was actually 3 periods of unusual cold weather that went from the 1300s to the 1800s, right? Now, during that period of time, glaciers worldwide got bigger than they had been in 10,000 years, right?
Whoa.
After the big glaciers melted, the climate of the planet went into the hypsothermal or climatic optimum, which was actually warmer, considerably warmer than the world is today. The glaciers shrank back to a great deal. They shrank back. So the great ice sheets over Canada were gone, right? But now the mountain glaciers in Canada, in Alaska, in Europe, in Russia, they all, even like down in New Zealand where they have mountain glaciers on the South Island, all these glaciers began to grow, and they grew to their largest extent since the Great Ice Age ended, right? So what we have here is like this little window into by the fact that our science and technology and industry came along at the end of the Little Ice Age. It has afforded us this opportunity to see a miniature version of glacier recession. You see, because the glaciers began to recede in the early to mid-1800s. And they've been doing that continuously and until now. They're still doing that, see? That's the thing that people don't understand. They think, they've only been receding in the last 20 or 30 years or whatever. No, they've been receding for 150 to 200 years, see? And they're receding from the biggest they've been in 10,000 years.
Right.
Right? So people just don't understand this. But now let's get back to the recession or the disappearance of the huge ice mass at the Lake Wisconsin. Now, when we saw the glaciers receding during the Little Ice Age, there was nothing like, even then, there was nothing like 850 feet per year, year after year after year after year, right?
Right.
It hasn't even been remotely like that. But see, so that in itself, it's like, where does the energy come from to drive that much melting? Well, so they did some calculations, and like, so here's what he goes on to say in this paper. He says this paper is mainly concerned with the rates of marginal recession of the Laurentide ice sheet, right? Which was the name of the big ice sheet over eastern Canada.
Right.
There was a separate ice sheet over the Canadian Rockies, the Cordilleran. But he says the marginal recession of the Laurentide ice sheet with particular emphasis on the retreat rates experienced during the deglaciation of the northern United States and southern Canada and the Canadian Arctic. Of primary concern is the energy balance at the margin of the ice sheet required to promote the rapid Lake Wisconsin retreat. So that was it. That was the primary concern, and it was the primary concern of this conference that was taking place back in 1973, where they're going, wait a second, if the ice was gone this quickly, how in the world, where was the energy that melted that ice? You see, because right and see, even in Canada today, there's no ice sheet. There's a lot of snow, but come spring, that snow melts away. It doesn't endure. It doesn't just stay there underground and not melt. And then next year, another 4, 5, 6 feet of snow is dumped, and then the next year, see, that's the problem of coming on an ice age. You see, it's
right.
Like you have to switch gears. You have to it's like a switch is thrown, and then all of a sudden now, hey, spring, it's winter, but spring doesn't come for 10 or 20,000 years. Yeah. You see, by the end of that, now you've got a mile or 2 miles of ice. Now, reverse it, flip the switch again, and you got to get rid of that ice. But you got to get rid of it literally in a few thousand years. So in the early 70s, this was the thing that they were beginning to confront. And he goes on to say, right here, and this hasn't changed since then. The growth and development of the Laurentide ice sheet complex is still an enigma. Unexplained is the growth of the ice cap in its gathering grounds of Baffin Island, Labrador, and Keewatin, where at least today there are low winter accumulation regimes. Equally unexplained is the southward penetration of the ice sheet to latitude 40 degrees north or so, where, even under full glacial climatic conditions, mass loss at the southern margin must have been considerable. So, see, here's the thing. It's like this huge conveyor, and it's moving this ice out of Canada in every direction. If you look at Hudson Bay, you'll see Baffin Island, Labrador, and Keewatin kind of form a rim around Hudson Bay. And this is where the ice was accumulating, almost like the blob or something, and it just kept growing bigger and bigger and bigger, and it kept getting fed by precipitation in the form of snowfall. And here's the other enigma, see? Here's the problem. In order to have that kind of rapid accumulation of ice, year after year after year, until the pile is 1.5 miles thick, well, you've got to be evaporating water out of the ocean, see? Well, in order to evaporate that water out of the ocean, you got to have heat.
Right.
You see? So how is it? See, it's like one conundrum after another that we're confronted with here. See, how do you wait a minute? If you've got all this extra heat to evaporate all of this water, then how is it that it covers millions of square miles but doesn't melt away?
Right.
See, nothing here makes sense.
Didn't you
wait a minute? Go on.
Does it not make sense in terms of like what the standard model, these modern scientists are trying to tell us, or because it seems to me to kind of make sense when you consider that there are these cosmic forces, and it's not this uniformitarian one drop of water, one grain of sand at a time thing. Like there are bigger actors at play here, namely the sun, when it comes to warming things up. Right.
Well, see, this is the thing. You guys you're going in the right direction. I mean, because we can study this thing and we can wrestle with it for decades and years like they have without coming to any solution. As long as we're confined to these like limited terrestrial sources of energy. But as soon as we're willing to expand our thinking into the cosmic domain, the whole scenario changes, you see.
Exactly.
Because, yes, now we have the possibility of solar activity on a scale that we maybe have not experienced in modern times. We have the possibility of impacts from things from space, which this is, to me, one of the most important realms of scientific inquiry going on now, is the danger that this planet is constantly in from the flux of material in space, right? But it hardly ever gets talked about. Every few months there'll be a close flyby, and it's almost become routine now. Some half-mile object is just outside the orbit of the moon and flies by. Oh, well, another close call. Well, to me, right now, we've really had the whole discussion of climate change and global change and so on has been hijacked. I'll just come right out and say it. It has been hijacked.
Yes, absolutely.
Mm-hmm. And actually, it could turn out that that's not such a good thing, because there are other things going on. And to assume that, that humankind is now in the driver's seat and that's the full explanation of climate change. No, that is a conceit, and I think it's going to end up to be the ultimate hubris if we don't realize. Wait a second, no, we are still minimal nothings when it comes to the forces of nature, and to imagine that now we're the dominant force driving global change? No.
Right.
People who believe that have no concept of the history of this planet upon which we live.
Absolutely.
Yeah. So I just saw, I guess it was a couple of weeks ago, a story, and I can't remember who did. I reported it on the podcast, but it was these guys, these scientists were studying the little ice age that you were just talking about, and they actually found out they got this old data from like the 17 or 1800s or somewhere, that these older scientists were dropping thermometers way down into the deep oceans in the Pacific and measuring the temperature and everything. So they got all this really old temperature data from the deep ocean Pacific, and then they compared it, they calibrated it, and then they compared it to today, and they found out that the deep Pacific Ocean is still getting colder from the little ice age.
Mm-hmm.
I thought that was...
Yeah, yes, it is, right. So there are lag periods, see, and now we've been in a period for the last 3 years of very low solar activity.
Right.
And it's clear from the evidence that, yes, that the coolings and warmings of the Earth are tracking the sun, and tracking the sun way more than they are carbon dioxide. In fact, it's carbon dioxide that's tracking temperature changes on the Earth and not the other way around. Because when the Earth heats, like, I'll put it this way, if the sun warms the Earth, the oceans absorb that warmth. It decreases the solubility of carbon dioxide that's in the oceans, and the oceans begin to outgas. When the planet cools and the ocean cools, it starts sucking in the carbon dioxide. So the oceans are exhaling and inhaling carbon dioxide in tandem, in tempo with the changes in solar output. Does that make sense?
Yeah. It does.
And so what we've done through our burning of fossil fuels has added to the natural carbon dioxide increase in the atmosphere because of ocean exhaling, because of post-Little Ice Age warming. But the problem is we're starting at such a low, in the history of this planet, almost the entire history of this planet, the amount of carbon dioxide in the atmosphere has been 3, 4, 5, 10 times greater than it is now. And what we see is that during these periods, like during the late Wisconsin, okay, for example, if the ice core records are accurate, there was a point at which carbon dioxide got down to 200 parts per million or lower. And you know what happens if carbon dioxide concentrations in the atmosphere get lower than 200 parts per million?
Like,
what do you think happens?
Plants die.
What is the main role of... Yes, plants begin to die.
Yes.
And in fact, for anybody who studies carbon dioxide and realizes, for the same reason that professional greenhouse growers will pump up carbon dioxide to 1,000, 1,200 parts per million, because plants are more robust, they're healthier, they grow faster, and so on. And virtually all commercial greenhouses will enrich the interior atmosphere of the greenhouse with carbon dioxide. Why do they do that? Well, what they're actually doing is they're pumping up the greenhouse concentrations inside the greenhouse to typically what they have been through most of Earth history until the cycle of ice ages began. And then the percentages of carbon dioxide in the atmosphere dropped from typically 500 to 1,000 or 1,200 parts per million down to 200 parts per million, right?
Yeah.
So at that point, you see, there's some studies now that would suggest that maybe this is one reason that we didn't see the birth of agriculture until 8,000 or 9,000 years ago, was because carbon dioxide concentrations in the atmosphere were too low to grow food crops. See, I mean,
That's crazy. Okay, so I do have a question on that end, and it has to do with the Pleistocene fauna, the megafauna. I've always wondered about what kind of biomass was required to support such enormous populations of such enormous animals.
Yes, well, they were, here's the other interesting thing, too, and here's more conundrums. There was a huge concentration of megamammals, megafauna in Siberia.
Yeah.
While North America was under the ice sheet, right? So how does that make sense?
Yeah, that doesn't make any sense at all. How was Siberia like temperate or whatever when?
Yeah, I mean, right. See, but
what do you think?
I mean, is this.
Yeah, okay. That's what I was going to say. What do you think the answer is? Is there one? Do you have a possibility?
I only have a hypothesis that needs to be tested.
Right.
But that would be simply going back to the conversation we had earlier about isostasy.
Oh.
Because the Earth is spinning on its axis, right? And it's not 100% rigid. It's a more or less plastic medium when looked at homogeneously. With spinning on its axis, what it does is the mass migrates towards the equator, right? So the equatorial diameter of the Earth is about 7,926 miles. The polar diameter is about 7,900 miles. So there's a 26-mile difference between polar diameter and equatorial diameter, or about a 13-mile difference in radius. So if you were at the center of the Earth and you were going to have to dig your way to the surface, you'd get there, you'd have 13 miles less of digging to do if you dug along the polar axis rather than at the equator. So now, picture this. Land mass is distributed in latitude according to several factors. One is its distance from the Earth's center of mass. You see, Now, if the Earth is spinning and all of a sudden you pile, in a geological sense, all of a sudden you pile up, trillions and trillions of tons of ice on one part of the Earth, does that affect the rotation? And the answer is, I absolutely think it has to. It has to affect the rotation.
Yeah, basic physics implies that it should. Yes.
Yes, but the question is how much?
Right. Exactly.
Right. And I have not found any studies yet that would suggest they've really looked at that. How the presence of a huge mass of ice that might be up to 1.5 miles, 2 miles thick would affect rotation. Well, likewise, when you melt that ice and remove it, and it goes back into the ocean basins, it has to affect the rotation. Now, what the planet is trying to do, by the fact that it's bulging around the equator, is it's always trying to maintain equilibrium. And so, just like any system, if something causes disequilibrium, and then the force that caused the disequilibrium is removed, the system will attempt to restore the original equilibrium.
Right.
Now, picture that if you're removing the lid of ice, and now the land surface, the rock, the lithosphere below it begins to rebound 1,000 feet, 2,000 feet, right? What happens? Is there possibly a lateral motion that has to take place to compensate for that increasing or decreasing distance from the center of mass? Because what the planet is trying to do is to homogeneously and uniformly distribute its mass about its center of gravity, see? So if something disturbs that, then the planet will have to try to eventually readjust. So when you remove the ocean, when you remove the ice from the land comes back. It goes into the ocean basin. Now, what do you think is going to happen to the floor of the ocean basin when you put these trillions of tons of weight back in?
They're going to sink.
They're going to sink. That's exactly right. And in fact, the empirical data has been gathered since the 1940s that suggests that there has been enormous isostatic compensation particularly along the suture zones, like, for example, the Mid-Atlantic Ridge, which shows evidence of considerable vertical displacement since the end of the last ice age. So now, what I'm getting at is when all of this surface redistribution takes place, now you've got portions of the surface of the Earth that are not in an equilibrium position with respect to the Earth's center of gravity. So now the natural tendency would be for them to try to migrate to where they should be. So, for example, if you're looking at the area around Hudson Bay and it's suddenly no longer the equilibrium distance from the Earth's center of mass, what's it going to try to do? So if you start moving it 2,000 feet or a half a mile away from where it had been in quasi-equilibrium, now what it's going to try to do in order to redistribute the mass uniformly is it's going to try to migrate towards the equator. Does that make sense? Because, look, if it rises a half a mile, now it's no longer in the position that it needed to be a half a mile. Because picture, you're going 90 degrees from the equator and you're up to the pole, and in that arc, you've moved 13 miles closer to the center of the Earth, right? So if you change the distance of a particular rock mass, and now suddenly it's 2,000 feet higher than it should be, or 2,000 feet lower. See, that then could set up lateral stresses that move latitudinally or longitudinally in order to try to. So, picture, interestingly, and this is what Charles Hapgood was noticing way back in the 1950s, that if you took the known distribution of the great ice mass, which was pretty much centered on Hudson Bay, and you drew a circle around it, that circle would be almost the same size as the Arctic Circle, you see? No. So he theorized that, well, Hudson Bay was the North Pole. And the ice around the North Pole, which was greater than the ice mass that is now in the South Pole, pretty much reached to just beyond what would have then been the Arctic Circle, and that's where it stopped. And if you move the crust of the Earth so that Hudson Bay moves up to the North Pole, you make that shift along that great circle arc, then it means that Siberia has moved in the other direction and has actually moved south.
Right. So
what he was theorizing was a short-lived period of accelerated plate tectonics. And he introduced this idea at a time when plate tectonics, or lateral motion of the Earth's plates, was only just beginning to be accepted.
Yeah. And
he was generally consigned to the fringe. But he didn't really have a mechanism for driving those lateral motions. And to me, it would make sense that this inconceivably massive redistribution of surface weight could be a force that could drive those kinds of adjustments. So in other words, as Hudson Bay began to move away from the center of the Earth's mass, it migrated southward to try to reach equilibrium, because now suddenly it's 2,000 feet farther away than it had been, right? Well, the pole is not the place for that, because you want no more than 7,900 miles at the pole. So if you actually go, 10 degrees or 15 degrees south, you're going to find a place where a mass of rock that is that far from the Earth's center should actually be. See, I know it sounds kind of convoluted and complex what I'm trying to explain, but I think you get the general idea. Right?
Yeah, I think what you're saying basically is that when you lift that weight off all of that rock, and it then rebounds and then is thus farther away from the center of Earth's center, then it wants to drift and get in the right spot on the surface where that weight is equalized, right?
Yes.
Okay.
Yes.
Yeah, that's really cool.
And we,
holy smokes.
Yes.
Okay. So yeah, I mean, there's a lot we're just on the verge of figuring out. That's why I really get irritated when I hear somebody saying it. All the science is settled.
Right.
Yeah.
Science is never settled.
No, it ain't. No, it's never settled. It is never settled. And consensus is meaningless in science. Because the job of, yes, it appears that we have a consensus. Once you get to that point, then it should be the primary job should be, well, let's try to rip this consensus apart and see if, when the dust clears, if it's still a consensus, right?
Yes.
That hadn't been done. That hasn't been. It was declared a consensus, and the research was declared over. Essentially, the conclusion preceded the research. Let me put it that way.
Yeah, we're big proponents.
And that's what
we're big proponents here of the idea of falsification rather than looking for proof.
Yeah, and consensus is for courtrooms,
that's exactly
juries.
Yeah.
Yes, exactly. All right, Randall, we've hit up on an hour here. Let us take a short break, and we want to try to get the watcher in on this call so that he can listen in. Is that all right?
Yeah. How long is that? Yeah, I'll get up and go have a snack or something.
Ladies and gentlemen, we are back. Brothers of the Serpent podcast with Randall Carlson, and we are having all kinds of technical difficulties and handling all of them flawlessly. Zero mistakes. All right, Randall, let's yeah.
Yes. Well, I want to apologize to you guys for the technical difficulties because it's what happens when I start thinking too hard and I get too excited. So I'm gonna try to rein it in here on my end and
yeah, your
try to calm down a little bit.
Your brain's blowing all the computer electronics around us, man. So one of the things I wanted to ask you was because I think that you're just fantastic at doing this is like let's say that from the perspective of the like say the Clovis people or any of the humans that were around when this Younger Dryas thing kicked off, when these cataclysms kicked off, what would they see? What are the things that would be happening? What would it look like to a person then and somebody trying to survive? What is that like?
Well, it depends, really on if you're in the right place at the right time, because see, the problem with impact phenomena is typically if it's anything much more than, say, the Tunguska event of 1908, there wouldn't be any witnesses in the aftermath. Anybody who was able to see the thing would be dead afterwards. From any number of things, from the overpressure, from the heat, secondary consequences. But obviously, people did survive because otherwise we wouldn't be having this conversation right now.
Right.
So that's pretty convincing evidence that somebody survived. So
it can be done.
All right, so maybe I should phrase it this way: what would it look like for people who may not have survived? I'm just saying, like, what would it be like on the ground? Is what I'm asking, I guess.
Yeah, it would have been a really scary place. I would actually rather be in a space. I'd like to be up on the International Space Station while it was going on.
Absolutely.
So, well, I mean, God, where would I even? A question like that you could actually answer by writing a whole book about.
Lay it on us.
Because listen, there was no place on Earth that came through unscathed.
Right.
But the problem is that there was a whole range there were definitely places of refuge because, in ecology, whenever there is a major habitat destruction that takes place, right? Now, this could be attributed to a forest fire. It could be attributed to a volcanic eruption. It could be attributed to a tsunami that, wipes out an entire coastal ecosystem. There's always places that, for whatever just the fluke of in this complex, chaotic situation, manages to survive. Right? It's the term in ecology is a refugium. So like in the aftermath of Mount St. Helens, you saw that there were places where, you had this completely obliterated landscape, literally like as desolate as the moon, for 200 square miles in the aftermath of that May eruption of Mount St. Helens back in 1980, right? Well, as it is now, nature is quite rapidly reclaiming that devastated landscape. But what you see is there'll be like pockets, pockets of life, pockets of green, and then it radiates out from there. Particularly colonizer species go out that are usually some species of fern, and then the ferns exist for a number of seasons, and by their death and recycling into the volcanic ash, it creates the conditions for the next generation of plant life. And then it proceeds through that until you get to a climax state, which is usually, depending on where on the earth it is, it could be old growth forests or whatever. Now, one of the things is that, there are a number of questions about, for example, the Carolina Bays in southeastern United States, which are these huge elliptical depressions in the land surface that have long axes that are generally parallel. And there's a lot of controversy over what formed these things. There's thousands of them, by the way, along the coastal plains. If you read Graham Hancock's book, in Magicians of the Gods, I'm pretty sure he talks about it in there. I know he's got it in his new book, America Before. There are some scientists, and I've met these scientists and talked to them, that believe it's, a longer process that has taken place, and they have their arguments for why they think so, that it has nothing to do with any kind of impact or anything like that. And there are others who think that they are related to impacts or impact craters of some type. This has been the Carolina Bays. You can look them up online. You'll see these remarkable images of these elliptical depressions along in South Carolina and North Carolina. They're typically very swampy because of their fact that they're kind of depressed around. They become places where water forms and peat forms, where water accumulates and peat forms. Okay. They also have very interesting flora and fauna in them that is unique. Like, for example, Venus flytraps, which are the predatory plants.
Oh, yeah.
Right. They grow in fact, that's where they're found, is in these Carolina Bays. Now, I tend towards the idea that Carolina Bays were probably extraterrestrial in origin, because I look at my studies of the Tunguska event showed that one of the things that they showed was that there were elliptical depressions under the epicenter of that atmospheric explosion. And I would lean towards the model that each one of these, what we're basically seeing there is, like, shall I say, a swarm of thousands of Tunguska objects coming into the atmosphere, and essentially blowing up in the atmosphere, and a conical shock wave intersects the sandy coastal plains and is able to essentially, it's almost like a blowout hole. The pressure pushes the sand because it's all on the coastal plain. Right. But again, it's very controversial. But if that scenario is true, then, that would have been pretty much the end of anything that lived in the southeastern United States. Yeah. In fact, I know they've found Carolina Bay formations in Nebraska whose orientation is different than the orientation. This is something that's easier to show pictures. I'm going to have a lot of graphics showing these Carolina Bays and how the orientation changes. You move from, say, actually there are some of the northernmost ones are up in Virginia, and then you come through North Carolina, then South Carolina, and then into Georgia, and always they're along the coastal plain, which is the area between the coast of the Atlantic Ocean and the Piedmont. So what you got is thousands of these things, but the angle of the long axis of the ellipse is slowly shifting, so that when you get into South Georgia, they're almost pointing north-south. Whereas if you're up in North Carolina, they're almost pointing northwest-southeast, see? Right. Then if you look at the ones in Nebraska, their axis is aligned northeast southwest. So when you take these long axes and you extend them, they all generally reach a point, kind of a point of convergence over northern Michigan or somewhere up in that area, which suggests potentially what? I don't know. Now, there's one theory. Tony Zamora believes that there was an impact there, a major impact, and the Carolina Bays were thousands of ice boulders that were thrown out from that impact that rained back down.
That's an amazing mental picture right there.
Yeah, and terrifying.
Yeah. Now, other scientists like Malcolm LeCompte, who I know, who we got on the Rogan show with us as our consultant when we did the debate with Michael Shermer, he doesn't believe that. I'm not sure what he believes, but he doesn't. And in fact, he may believe that they're cosmically have a cosmic origin, but I don't think he does, because Chris Moore, who's another scientist who's a geologist that's been working on this, he's one of the ones who actually believes that there was a Younger Dryas impact, for sure. And so does Malcolm LeCompte. They just don't think that the Carolina Bays were part of it. Now, Tony Zamora and several others do. And, it's just going to have to be debated out. And I don't see any resolution to it anytime soon, because unless we have some conceptual or evidentiary breakthrough, I don't see the controversy getting resolved. Although my idea is not originated with me, because this controversy literally goes back to the 1930s when aerial photographs of these things were first taken, and geologists who looked at it came to believe that it was caused by like a giant meteor shower, because that's the only way they could think of to explain it, and to explain the ellipses, to explain the orientation of the long axes. I was just really obsessively interested in the bays really back in, when would that have been? I took an aerial flight. I hired a pilot to fly me over the Carolina Bays, and that had to have been 20 years ago, maybe longer. So yeah, my interest in them goes back certainly into the early 1980s. So at one point, when I was researching the bays, and because I live in Georgia, I had ready access to them. So there's a whole flock of the Carolina Bays in South Georgia that I went and visited on foot, and did this one aerial overflight. And I have photographs of that. But at that point, I'm still inclined to the original idea, which was that seemed to make the most sense to me, was that it would be a fragmenting comet nucleus that spawned thousands of Tunguska-sized objects that then entered the atmosphere and exploded, and the shock waves of their explosions, which actually would form as they're entering the atmosphere, the air is going to pile up in front of them and form a conical shock wave. This is basic physics that's pretty well known by meteor scientists, right? So if that thing is coming in and there's a conical shock front and the atmosphere is piling up in front of it, and then it explodes, right? And you can almost imagine like I guess what would you like? Super compressed air or something, hitting the ground and gouging out these depressions, which to me still seems to be, and only because it theoretically you can kind of make it work, but also empirically, elliptical depressions were found under the Tunguska epicenter.
Right.
So, but it's, again, I'm not going to say, oh, that's it, I've got it all figured out, because I don't. But that would be, I just don't know about Zamora's idea. I don't know. I haven't thought it through. I haven't tried to understand the physics of it, whether ice blocks could survive passage through the atmosphere. He did then ran the numbers and thought that they could. I want to see, I have not looked at Malcolm LeCompte's refutation of the ice boulder hypothesis. So I can't put any stock in it, because I'm not familiar with what his objections are. I do know he objected to it, and his objection, when Graham did an interview with, I think he did an interview with Zamora, or he did something and kind of caused a bit of a rift because of the ones that think that the Carolina Bays have a terrestrial origin. And then you have it's actually the same controversy that goes back to the 30s through the 40s and 50s when there were two camps that arose. One were referred to as the terrestrials and the other were the celestials, right?
Yeah.
So the celestials had variants on the idea that it was a meteor shower or a comet impact, an exploding comet, something like that. The terrestrials were centered around Douglas Johnson, who was the dean of geomorphology out of, where was he? Out of, probably, I think he was out of Harvard. And he made a whole study of the Carolina Bays, wrote a book called The Big Tome, which I actually did read the entire book cover to cover back in the 80s, called The Origin of the Carolina Bays. And what he came up with was what he called the complex theory. So in order to explain all of the vagaries and inconsistencies and weird things associated with the bays, he called it the complex theory. So he basically threw everything into the theory to come up with he called it the solution. Artesian solution Aeolian lacustrine hypothesis.
Oh my gosh.
Did you get that? Repeat that back to me.
Latesian, Latusia.